Okay, welcome aboard. This is the MATLAB coding course series titled How to IMU, part 2 of 3. I'm your instructor Steve, aka Heavy Hands. If you don't remember why they call me that, you'll find out in a minute. Last section we covered how to get data from our IMU and into MATLAB for a single manual read. We also talked about some conversion factors, but this time we're going forward with a new question, and that is, how do I live stream my IMU data? The problem that we have is that we need an original live stream code, and the solution is that we're going to break it down how to live stream your IMU data right now. The objectives for part 2 are as follows. Objective 1 is differentiating sensors within the IMU. Objective 2, we're going to live stream the acceleration data for 20 seconds. Objective 3, we're going to live stream all of the sensors, the entire IMU data, for 20 seconds. So we're going to be writing, well, 3 different sections here. The required hardware is the same as part 1, the Arduino Uno, the prototype shield, the BNO-055 9-axis IMU, the miniature breadboard, and your 4 jumper wires. The required software is the same, the MATLAB 2020 A or B, MATLAB support package for Arduino hardware, sensor fusion and tracking toolbox, and instrument control toolbox. The circuit layout hasn't changed either. If you need to recover any of this stuff, you can go back to part 1, where we cover it in more detail. Remember, we have 3 simple rules. Rule number 1, we do not rush towards failure. Rule number 2, slow is smooth and smooth is fast. And rule number 3, you know that we are here to drink water. Okay, let's call to order. Activate your brain housing group, open your long-range visual scanning portholes, and engage your primary weapon system. Here we go. Objective 1, differentiating sensors within the IMU. Let's get back to where we were before. That started with an A equals R. You know what? Let's just do this in the command window so we're not getting confused here. Let's reopen our A equals Arduino. When we call this variable out, we are going to be met with an A variable, which is equal to the Arduino board. And next we're going to say the IMU is equal to the BNO-055 of A. When we run that section, we are going to find the IMU. And next I'm just going to throw it in right here. We can clear our command window now. And we're going to give status. If you remember this from the last section, read calibration status of the IMU. You can go ahead and run that section until you have all of your sections as either full or partial. I think in the first section I got them all on the first try, so you didn't get to see what it looks like when it's not done the full out. I'm just going to try to maneuver my sensor around. There we go. I got all partials. Those are good. Remember, with time, this thing continues to recalibrate itself, and those partials will turn into fulls. So we can clear that, and I'm just going to make this in as a comment because it's not really part of this section. This was more section 1, so let's just move you out of the way. All right, objective 1 is differentiating sensors within the IMU. So what we need to start with is understanding that, remember, there are 3 sensors here. Remember, we're here to create this. 3 sensors, an accelerometer, a gyroscope, and a magnetometer. They each operate X, Y, and Z axes, and I want all of it. Not only that, I want the orientations also. I want those 3 things fused together, and I want to know angular position. So I'm really looking for 4 different streams of data here. So let's go ahead and start with a variable. IMU read is equal to read the IMU. When I run that section, I get my table, my 10 timestamps, acceleration, angular velocity or gyroscope, magnetic field or magnetometer, and my orientations. Remember, in the Z, Y, X. Z, Y, X for orientation. The others are X, Y, Z. Orientation is Z, Y, X. Okay, let's go ahead and suppress that. We're going to carry on, and we're going to say that that table is nice, but I'd really prefer to see it as a matrix. So my IMU matrix is going to be equal to my IMU read table, except as a matrix. If I go ahead, clear, and I run that section, I'm going to get my XYZ acceleration, XYZ gyroscope, XYZ magnetometer, and ZYX. ZYX orientation. It is imperative that you get that into your head, that column 10 is the Z-axis, column 11 is the Y, column 12 is the X. Okay, that's going to save us a lot of trouble in the future. So let's clear that. Now I have this matrix of the 10 samples. That's wonderful, but I really am only interested in one of them. So I'm going to say that the mean, the IMU mean, is equal to the mean of my IMU matrix. These three commands right here are going to produce those 10 timestamps averaged into one. XYZ acceleration, XYZ gyroscope, XYZ magnetometer, and ZYX orientation. Very good. If I go ahead and clear my command window and suppress this comment, I'm going to put in a little, or rather suppress that output. I'm going to put in a comment here, and I'm going to say these three are home base. This is where we start to pull all of our different sensors from. So let's go ahead and differentiate these sensors. We have an accelerometer. We have a gyroscope. We have a magnetometer. And we have an onboard fusion algorithm that is going to give us orientation. Let's talk about accelerometer in the x-axis. ACCX is going to be equal to the IMU mean in the first column. The ACCY is going to be equal to the IMU mean in the second column. The acceleration in the z-axis is going to be equal to the IMU mean of the third column. Carrying on to the gyroscope now, we have gyro x is going to be equal to the IMU mean of the fourth column. Our gyro y is going to be equal to the IMU mean in the fifth column. Oop, I've done that before. Yep, there we go. Gyro z is equal to the IMU mean of the sixth column. Good. Gyroscope is all squared away. Let's carry on. We're looking at our magnetometer next. That is not going to fly. Let's go ahead and switch that out. Our magnetometer in the X is going to be equal to the IMU mean of the seventh column. Our magnetometer in the Y is going to be equal to the IMU mean in the eighth. And our magnetometer in the Z is going to be equal to the IMU mean in the ninth. Good. Y, okay, very good. Now, orientation is coming from our fusion algorithm. ORT X is going to be equal to the IMU mean in the 12th. And the orientation in the Y is going to be equal to the IMU mean in the 11th. You couldn't have got that one wrong even if you tried. And the orientation Z is equal to the IMU mean, oops, not OIMU, just IMU. Just IMU mean in the 10th. Very good. Now, that's going to break down how to stream every single piece of data that this IMU is capable of catching for you in terms of motion. Now let's go ahead and take a look at this here. This acceleration X is the IMU mean in the first, acceleration Y is the IU mean in the second, acceleration Z is the IU mean in the third. Very good. Gyro X is the IMU mean in the fourth, gyro Y in the fifth, gyro Z in the sixth. Very good. Magnetometer X in the seventh, magnetometer Y in the eighth, magnetometer Z in the ninth, and now we're talking orientation, and the X is coming in at the 12th, the Y in the 11th, and the Z in the 10th. Very good. Now let's be a little more specific here. This acceleration is coming in meters per second squared. This is coming in meters per second squared, and this is coming in meters per second squared. This is coming in radians per second, this is coming in radians per second, and this is coming in radians per second. The magnetometer is always coming in microteslas, and we're happy with that. The orientation is coming in radians for all of them. Very good. Now, let's say we wanted to do some conversions. We wanted ACC in the X in terms of g-forces. We're just going to take the ACCX variable in meters per second, and we're going to divide it by 9.81. And then we're going to go ahead and take ACCY in g-forces is going to be our acceleration y variable divided by 9.81. And then we're going to take our ACC in the z in g-forces is equal to the ACC z in meters per second divided by 9.81. Okay, accelerometer all squared away right here. If you want meters per second or g-forces, we're all set. Next, moving on to the gyro, we might want our gyro in degrees per second rather than radians, so our gyro x degrees is going to be equal to our gyro x radians times 180 over pi, 4159. And then our gyro y degrees is going to be equal to the gyro y radians times 180 over pi. Next, we will have gyro z degrees is going to be equal to the gyro z radians times 180 over pi. Excellent. As we said before, our magnetometer is coming in microteslas. We're happy with that. Orientation is coming in radians, and we might want it in degrees. So let's go ahead and say ORTX degrees is equal to ORT radians. Put a little bracket on there. Times 180 over pi. And then we're going to say the ORTY in degrees is equal to the ORTY radians times 180 over pi. Finally, our orientation z degrees is going to be equal to the orientation z radians times 180 over pi. Good. Okay, so take a look at this section right here. 1, 2, 3, we have our basic setup for home base. Accelerometer in meters per second or g-forces, whichever you prefer. Gyroscope in radians per second or in degrees per second, whichever you prefer. Magnetometer is coming in microteslas. If you want to convert it into something else, you have plenty of how to do that so far. So if you want to change it, go for it, but we're not going to. Orientation is coming in radians in just radians, but I definitely want it in degrees, so we converted those over also. All right, section 1, how to differentiate the different sensors within your IMU. All set. Let's move on to section 2. Objective 2, live stream accelerometer. All right, objective 2, live stream acceleration data for 20 seconds. This is going to be what we were talking about with the streaming actually coming in live in the command window right here, which is I think what we're all here looking for. So let's go ahead and start with a counting variable. It's going to be ACC count, and that's going to be equal to 0. And then I'm going to want to store all my data somewhere, so I'm going to say that my ACC data is equal to a matrix. That's just going to be empty right now. And next we're going to say while my ACC count is less than 200, because this thing reads at 10 samples per second, ergo 1 over is 20 seconds, 200. You see the conversion factor there. While that condition is true, I want my ACC count variable to increase by 1 for each iteration. That's great. Next, we are going to establish our home base. Home base included the IMU read variable, which was equal to read my IMU. Next came the IMU matrix, because we don't want the table, we want the matrix, is equal to the IMU read just as a matrix. Next, we are going to say IMU mean gives us the average of the IMU matrix. That makes it much easier for us to stream out data plots. Let's go ahead and carry on. Next, we're talking about accelerometer data. ACCLROMET, accelerometer data. Now, I showed you how to do conversions for g-forces, but for the sake of this loop right now, we're going to be using it in meters per second. So I'm just going to say ACCX meters per second is equal to the IMU mean of all in the first. Very good. My ACCY in meters per second is equal to the IMU mean in the second. And my ACCZ meters per second is equal to the IMU mean in the third. Good. Okay. Now, these variables are going to be going through these iterations based on this iteration count. This is really annoying, so we know that we're going to have an end statement there, and that's just annoying. Let's just put it in there for now. Okay, but I want to add a site because let's not get concerned with what's happening at the end. Let's continue on with the center. I have a variable counter, it equals 0. I have an empty matrix. I have a condition that while my counting variable, which is currently equal to 0, is less than 200, it's going to increase with each while loop iteration by 1. Inside of this while loop, I'm reading the IMU, I'm turning it into the matrix, and I'm taking the average of the matrix. Then I'm differentiating the sensor specifically into the accelerometer by calling out its specified columns from the IMU mean matrix, which is 1, 2, 3 for X, Y, Z. Now, while this is happening, I'm definitely going to want to capture this data. Capture the data silently. Okay, to capture the data silently, I'm going to reintroduce my ACC data. My ACC data is definitely going to be a matrix, and it is going to be filled with the following information. I want my counting variable. I want my ACC count. I want my ACCX in meters per second. I want my ACCY in meters per second, and I want my ACCZ in meters per second. Okay, but I'm going to suppress it. Now, the reason I'm suppressing it is because if I tried to stream this, I would see one iteration, then I'd see iterations 1 and 2, then I'd see iterations 1, 2, and 3, then I'd see iterations 1, 2, 3, and 4, and it gets really, really messy after that, since especially because we're going up to 200. So instead of this, I'm going to introduce a new variable called, well, I'm not going to get to the variable yet, but it's going to say what will I see in the command window. In the command window. Or I guess it's not really a question, it's more what I will see. What I will see in the command window. It's not a question, it's a statement. And that is going to be show me acceleration. Show me acceleration is going to be a matrix. It's going to include the ACCX meters per second, it's going to include the ACCY meters per second, and it's going to include the ACCZ meters per second. Now, I don't know what you're thinking, but if you're thinking, hey, didn't we just kind of do that? Yes, we did, except now we are not including this counting variable, which means we're not counting iterations with show me acceleration. This variable is specifically here to show you some command window stuff. You can see that I suppressed it because I don't need to see show me acceleration equals brackets each time it iterates through. I just need to see this right here. So to make that happen the way we want it, I'm just going to display show me acceleration. And I'll suppress. Okay, moving on. Now we're going to need to figure out a way to finish this out when we get to our spot. So I'm going to say if my ACC count is equal to 200, that was our iteration number, then I'm going to want to display this is the end of the accelerometer session. That'll work. And I'm just going to end it. The loop is going to terminate when we get to 200 iterations with this statement. This is the end of the accelerometer session. Okay, now I can go ahead and scroll up here. We did some, I didn't want to see it earlier, but I do want to see it now. I need to end my while loop. I didn't want these two end statements getting confused. That's why I put it all the way down there. At the end of my while loop, I'm going to want to capture what I was going for. So let's go ahead and pull out my ACC data from the final iteration, and let's just suppress it. And then let's say my acceleration table is going to be equal to array to table of the ACC data with the following variable names. We have time. We have time in 0.1 seconds. We have acceleration in the x-axis. We have acceleration in the y-axis. And we have acceleration in the z-axis. I'm not going to suppress the table because I do want to see it. And let me just run a comb through this real quick. Here we go. Let's check it out. ACC count is a variable. What is the variable? It is equal to 0. It is a counting variable. We have another variable here, ACC data. What is this? It's an empty matrix. Okay. And now I'm starting this while loop. What's the condition? The condition is that while my counting variable, which is 0, is less than 200, it will increase by 1. 1, 2, 3, 4, 5, 6, 7, and up to 200. Very good. Now each time it iterates, it is going to read the IMU. It is going to convert the IMU into a matrix and then take the average of that matrix. All of these things are suppressed. We're pulling the acceleration in the x-axis in meters per second from the first column, the y-axis from the second column, and the z-axis from the third. Then we are going to reintroduce our ACC empty data matrix, and we are going to fill it up with the counting variable, the x-axis acceleration, the y-axis, and the z-axis. Now we're suppressing that because we don't want to see the iteration counter in the command window. What we do want to see is this variable that we made here called show me acceleration. And that is a matrix containing simply the x, y, and z accelerations from the IMU. And then we're displaying show me acceleration because I don't want to see the variable name popping up each time. When the accelerometer count gets to 200, the loop will terminate with the statement displaying this is the end of the accelerometer session. Cool. All right, so let's go ahead and, and then we ended our loop, grabbed the ACC data from here, and we converted it into a table with the following variable names: time in 0.1 seconds because it's 10 iterations per second, acceleration x, acceleration y, acceleration z. I didn't suppress it so that we'd be able to see. Okay, let's go ahead and give this loop a run. I'll grab my IMU here, and let's run section. Here we are, off to the races, iterations flying through x, y, and z. I'm holding this as flat as I can. It should be about 9.8 since we're in meters per second, and yeah, we're pretty close, pretty accurate. And if I do some other movements now, you'll start to see that those gravitational vectors are changing. Okay, let's go ahead and scroll on up. What happened here? We got a whole mess of data. Coming in, all about 9.8s. And then I started wiggling the gyroscope around in all different directions, changing the acceleration vectors. Oh, I even got it up to 10. Look at that. That's interesting. And iterations carried on until we got to 200, to which it said this is the end of the accelerometer session. The data matrix was captured and suppressed, and it produced this really nice table for me right here. All my time iterations and my x, y, and z's. All right, great. Let's carry on to section 3. Clearing the command window, clearing all variables that don't have specifically to do with calibrating or identifying the IMU, the Arduino, so that we can do them all fresh each time. You could just do, if you're going to do these, you do clear, whatever, right there. But for right now, we just did that one accelerometer loop. Very good. Objective 3. Live stream all of the IMU data for 20 seconds. Okay. This is going to be very similar to Objective 2. Let's start with a counting variable. IMU count is equal to 0. We're going to need a matrix to put this all in. IMU data is equal to an empty matrix. Next, while my while my IMU count is less than 200 for 20 seconds, I want my IMU count to increase by 1. While that happens, I need home base. I need alignment first, and then I need home base. Oops. Home base was the IMU read is equal to read my IMU. And then I need to convert that into a matrix. I need my IMU matrix is equal to my IMU read just as a matrix. And then I need to take the average of those. My IMU mean is equal to the mean of the IMU matrix. Very good. Okay. Now, in section 1, we talked about differentiating all of the sensors. When you suppress data inside of a while loop, it's kind of like it's not even there unless you call it back out after the fact. So what we're going to do is just go on up to section 1, objective number 1, differentiating sensors. We have our home base here. Let's just go ahead and bring all of these right down and into our while loop. Of course you're going to do that to me. Well, very good. We need to talk about them anyway. The first thing we're bringing in is the accelerometer. It is coming in meters per second initially, and we are going to be able to convert it over to g-forces if you want them that way. Next, not just next, let me align everything. Next, coming in is our gyroscope. The gyroscope is coming in radians per second, which you can convert into degrees per second if you choose. And let's go up there. It all depends on which variable you want to call out when we do our show me section. And the magnetometer is going to align. And finally our orientation, which you remember was Z, Y, X. That's why it says 12, 11, 10. Don't get it twisted. We convert that into degrees. Very good. Okay, now all of our IMU data is inside of the while loop with conversions. So we are going to go ahead and call out our variable of IMU data is going to be equal to a matrix with the following columns. It's going to have the counting variable. It is going to have, we're going to do meters per second, like I said. We're doing ACCX meters per second. We're doing ACCY meters per second, and we're doing ACCZ meters per second. We are also doing gyro X in radians. We are going to do gyro Y in radians. We are going to do gyro Z in radians. We are going to do mag X. We are going to do mag Y. And we are going to do mag Z. Then we are going to finally add in orientation X degrees, orientation Y in degrees, and orientation Z in degrees. We can close our matrix off, and let's go ahead and move on to a new line. Now that IMU data capture matrix, this is the capture, is suppressed. And next we are going into what I will see in the command window. What you're going to see in the command window is going to be a variable called show me IMU. And that variable is going to contain the following items. It is going to contain the acceleration x meters per second. It is going to contain the acceleration y meters per second. It is going to contain the acceleration z meters per second. It is going to contain the gyro x in radians. It is going to contain the gyro y in radians. It is going to contain the gyro z in radians. It is going to contain the magnetometer in the x, the magnetometer in the y, and the magnetometer in the z. And finally, it is going to contain the orientation in the x in degrees, the orientation in the y in degrees, and last but not least, the orientation in the z in degrees. I'm going to suppress that matrix because I don't need it to tell me that it's showing me the IMU each time, because I know that, and I'm just going to display show me the IMU. Now, I have my capture squared away, I have my display squared away. Next, I'm going to create my condition if my IMU count is equal to 200. I would like to display this is the end of the IMU session. And we'll suppress that and end. The loop will terminate, and then I can terminate my while loop. When the while loop is over, I want my IMU data. And not only do I want my IMU data, but I want my IMU table as array to table of the IMU data with the following variable names. Time in 0.1 second intervals. Next variable is the acceleration, ACCX. That's going to be in meters per second squared. I think I've been saying meters per second this whole time, but it's meters per second squared. Acceleration x, acceleration y, acceleration z. Then I'm going to take the gyro x, which is in radians, the gyro y, and the gyro z. Then I'm going to grab the magnetometer x, the magnetometer y, and the magnetometer z. And finally, I'm going to take the orientation in the x, the orientation in the y, and the orientation in the z. I can close that table off. I'm not going to suppress my table because I do want to see it. And now let's run through this from top to bottom, because we're not interested in making mistakes if we don't have to. We start with a variable, an IMU count is equal to 0, and then we open a new variable called the IMU data, which is an empty matrix. Okay. Then we are starting a while loop that says, with the condition that as long as the IMU count is less than 200, I want the IMU count to increase by 1. Okay. Then I'm going to home base, where I read the IMU, convert it to a matrix, and then take the mean of that matrix. Next, I'm pulling my accelerometer data in meters per second and in g-forces, and then I'll decide which one I want later. Next, I take my gyroscope data in radians per second, converted to degrees per second, and I'll decide which one I want later. Next is the magnetometer. It's coming in microteslas. That's fine for us right now. We're just going to take those. And finally, we take the orientation in the z, y, x as x, y, z. 12, 11, 10 is x, y, z. We're converting it to degrees, and then we'll decide which we're going to capture. I can widen this up so we don't have to, well, that's maybe not all the way. Next, I'm taking my empty matrix, and I'm going to fill it up with stuff. I'm going to fill it up with a counting variable. I'm going to fill it up with my acceleration in the x, y, and z in meters per second squared. I'm going to fill up my gyro in radians, x, y, and z. I'm going to fill it up with magnetometer, x, y, and z. And I'm going to fill it up with orientation in degrees. So this will be a good way to show you that you can take one in radians and the other in orientation degrees, and it's no big deal. That data capture matrix is being silenced because I don't need to see these iterations compiling on top of each other. What I would like to see, though, would be the acceleration in the x, y, and z in the first 3 columns, the gyroscope in radians, x, y, and z in the next 3 columns, the magnetometer in the x, y, and z in the next 3 columns, and the final 3 columns containing my orientation in the x, y, and z. So since I have those things all done now, I'm going to suppress the show me IMU matrix and just display the data. no variable name. And then I'm saying the condition that if my IMU count reaches 200, then we're going to say this is the end of the IMU session and the loop will terminate. I'm going to pull the IMU data back out of the end of the while loop and convert it into a table with the following variable names. Time is 0.1 seconds per iteration, so again 10 to 1. X, Y, and Z acceleration, X, Y, and Z gyroscope, X, Y, and Z magnetic fields, and X, Y, and Z orientations. Not suppressing it because I want to see it when it's all done. So let's go ahead and open my command window back up. Make it nice and wide here. Hopefully we can get all 12 in there. Let's even narrow you up and give us as much space as we can get. And let's go ahead and run this section. Here they are, acceleration X, Y, and Z. I'm a little tilted right now, so let me get her back to the 9s. I'm holding it up steady here. Then we're going into the gyroscope X, Y, and Z, the magnetometer X, Y, and Z, and the orientation X, Y, and Z. I'm going to tilt my guy to the right. Look at my orientation is now up in the 20s, and I'm going to tilt it back in the opposite direction. Oh, ran out of time. So here we go. Let's check out what we got from our command window. It started with this huge data stream of all of our points that we wanted. And then when we got to 200, it told us this is the end of the IMU session. It pulled the matrix out and then converted it into this really nice table here that just tells us where time, acceleration X, Y, and Z are, gyroscope X, Y, and Z, magnetic field X, Y, and Z, and orientation X, Y, and Z. Pull this back open. And that covers Objective 3. I hope you enjoyed Part 2. We'll see you again for Part 3. Bye.